Hello, and welcome to Lecture 4 of Motion in a Straight Line in Phys 1104. Up until now, we've been looking almost exclusively at situations where objects are moving with constant velocity, but now we're going to start looking at the slightly more complicated situation where the velocity is changing. Here's a motion diagram that I had you look at a few classes ago, and I didn't interpret it for you, I asked you to interpret it, and hopefully you've come to the decision that this is something moving in a circle, and hopefully you can also see that it's moving at a constant speed. So you could do this right now. You could get up and walk at as close to a constant speed as you can, in as close as you can to a perfect circle in your room. And now I've just added some labels to the points, including an initial and final label. And I'm going to ask two very different questions. First of all, what is your average velocity from Ti to Tf? And second of all, what's your velocity at time t2? Now, let's think about how you would actually go about answering these questions experimentally. So the average velocity we've been talking about, we know how to do that. You could measure your displacement from I to f. Now you just divide that displacement vector by the time it took you to get from I to f, and that is your average velocity vector from I to f. And we can restate that question. We've already done so earlier. It would go something like this. How fast would you have to go and in what direction to get to the same place, moving at constant speed in a straight line? Now that's a kind of complicated sounding question, isn't it? But the answer is this thing we call the average velocity. Now let's think about that other one, your velocity at time t2. Now we can rephrase it. How fast are you going and in what direction right now, where right now means t2. That seems like a simpler question, doesn't it? But how would you answer it? Well, in practice, what you might do is measure the circumference of the circle and measure the time it takes you to go around the circle, divide the one by the other. Now you know your speed, you believe you're going at constant speed, and so you can just say you're going at that speed in whichever direction you're headed at time t2, and you can now represent that as a vector, v2. But notice, even though the question seems simpler, that was a rather harder process to go through, and it involved an assumption that you were moving at constant speed. We had to model your motion to be able to answer the question, and that model may not be entirely accurate. So even though the question, what's your velocity at time t2, in some sense seems like it should be simpler than what's your average velocity between two times, it turns out that this is a slipperier question to get around. The thing we're calculating here, v2, would be called your instantaneous velocity at time t2. And throughout this course now, whenever we're talking about an instantaneous velocity, we'll tend to just say velocity. If I just say velocity, I mean the instantaneous velocity. If I mean average, I'll say average. And likewise, if I say speed, I just mean instantaneous speed. I'll say average speed if that's what I want. Let's look at a simpler motion that's in roughly a straight line. That's a better example of this for our current purposes. So here's one of the simplest ones we could do. I'm dropping a ball, and I'm using the video analysis software which you'll eventually use in the lab, and so I can generate a motion diagram and extract position versus time data from it. And I had to define axes and a scale to do that, and I'll just point out, because it's going to be important for understanding the data, that I've told it to use axes like this. And the reason for that is that the entire motion is downwards, and so it makes sense to make y positive downwards. It's just simpler. I've exported the data, put it into a spreadsheet, and graphed the y versus t data, and here it is. Now that we've seen this falling ball, let's think about how to answer the same sorts of questions about it as I was asking about the circular motion right at the beginning of the lecture. So let's think about the average y component of velocity from time 4 to time 9. The motion is nearly straight down. Let's ignore the horizontal motion and focus on the vertical. Well, we know how to do this. We would calculate the measure the displacement from time 4 to time 9. And note I'm calling it delta r 4,9 to specify which displacement I mean. It's the one from time 4 to time 9. We would now take the y component of that and divide it by the time it took for the ball to go from time 4 to time 9, and that gives us our average velocity y component from time 4 to time 9. So see, I'm keeping the 4,9 in the subscript instead of av to specify which average I mean. Let's check your understanding, since this is a key skill. So I've given you a table of data and a graph, and I want you to find the average y component of velocity of this ball from t equals 0.1 seconds to t equals 0.6 seconds.